Okay, so hi. This is revision material for phy221 classical physics, and the way I usually do this is I start with some introductory material which covers the material we actually went through in the lectures, and I give some general advice, and maybe I do some problems. And I'm doing it on YouTube because the exam is quite early in the season and some of you won't get back before the very beginning of next week, so it's not really fair to have revision lectures that some people can come to and other people cannot. So let's have the advice first, and it's always fairly similar advice every year. Read the exam paper. Right? It's a mistake to start the exam by scribbling, by doing question one, by frantically plowing through question one, because you'll probably make yourself nervous by going into it that way, and then there'll be a tendency to go, oh well, I should do question 2 and then question 3, and it may be that questions 1, 2 and 3 are not the easiest questions on the paper, or it may be that they are. But you owe it to yourself to look at each question carefully before you start and make a strategy, because that's how you're going to make the most effective use of your time in the exam. So please, everybody should read the paper before they start doing even the compulsory question. That's the first piece of advice. The second piece of advice is the night before the exam, do not stay up all night or very late night cramming. Get some sleep, have breakfast. If you usually have a cup of coffee, have a cup of coffee. If you usually have a cup of tea, have a cup of tea. Try to put yourself in good physical condition to do the exam, as well as prepare yourself mentally by doing revision. Okay, so the first topic we covered in the exam was the simple harmonic oscillator. And so for that you need the simple harmonic oscillator equation, and we're not going to derive it because it's a very general equation of motion which is valid for many different physical configurations of apparatus. And so we can just start by looking at the equation. So let's write it down. So what we have is the second derivative d2 y by dt squared equals minus omega naught squared y, where y is considered a function of t, and t is time, and y is a displacement. And so that's your equation. So the solutions of this equation can be written in different forms. I'm going to use both forms in going through this stuff. So the first form is to say that y of t is a constant times cos of omega naught t plus another constant times sine of omega naught t. So that's one way of writing the solution of the simple harmonic oscillator equation. This is called a general solution because A and B are constants determined by initial conditions. In other words, you only find out what A and B are by knowing the state of the oscillator at some time, and usually that time is t equals 0. You just define t equals 0 to be the time when you know the state of the oscillator. So you might say, for example, that at t equals 0, the oscillating body, whatever it is released from rest at displacement y0. And so if that turns out to be true, then let's consider the part of this general solution which is relevant to that, and that's the a cos omega t bit. So if you plot a cos omega naught t as a function of time, what you see is that it takes the form of a cosine where the amplitude, the peak amplitude of the cosine is A. Right? Notice that at time t equals 0, right, the slope of this line is 0. And that means that the oscillating body is starting out with no velocity. And then its velocity is getting bigger and bigger, and its velocity is negative because it's moving back towards the equilibrium position. You can tell its velocity is negative because the slope of this cos of omega t up until the point where it goes through y equals 0 is a negative slope, so that means it has a negative velocity. And then as it passes through the equilibrium position, it reaches a maximum magnitude of velocity, so it's going as fast as it ever is. And then once it goes through the equilibrium position, it starts to slow down, and you can tell that because although the slope is still non-zero, it's decreasing. The slope of y as a function of t is decreasing until here. Notice that the mass has stopped, and where it's stopped, it has exactly negative the displacement it started out with. So if it started out with a displacement a, it stops again first at displacement minus a. And that makes perfect sense because if you have an oscillator, let's say it's vertical, you release it from rest, it accelerates, it goes down, it goes to the equilibrium position and it stops. And because it hasn't lost any energy, there's no energy loss mechanism in this, it must eventually reach the same magnitude of displacement in the other side of the equilibrium position that it initially had. And then it starts to accelerate back towards the equilibrium position, reaches a maximum velocity magnitude here, and finally after one whole cycle of the oscillator it's back to where it started. Okay? So if you think about it, that motion is exactly what you'd expect for a body released from rest at displacement y0. So for this problem, this initial condition here, let's write it, let's call it an initial condition. That initial condition implies that y of t equals y naught cos of omega naught t. Right? This term here doesn't play any role. The reason why this term doesn't play any role is because if this b is non-zero, then the slope of y of t at t equals 0 would not be naught. The slope would be something other than 0, which means that that would correspond to an oscillator where the particle was given some initial non-zero velocity. But in this case, we've been told that the oscillating body is released from rest. In other words, at time t equals 0, it's not moving. And so this is the particular solution that corresponds to the initial conditions given here. I should actually write initial conditions because I should point out there are two conditions in this sentence. So you're told that at t equals 0, the oscillating body is released from rest. That's one initial condition. That tells you that dy by dt at t equals 0 is naught. And its initial displacement is y0. So that tells you that y at time t equals 0 equals y naught. So that brings me on to another little piece of advice for those of you who want to have a success on this exam. Read the sentences of the question carefully. It's easy when you're doing physics to too quickly zoom in on what you think are the key points in the question without bothering to read the words between what you think are the key points. Often the things students zoom in on are numbers. So if you see a number in the paragraph, your eyes might immediately zoom in on that number, when actually you're better off reading the sentence because there may be other information in the sentence that's contained in words as well as numbers. And indeed, it may be true that you need to read the words carefully to understand what a number means. So that, I think, is a good piece of advice as well.